Now we can talk about climate feedback mechanisms. What is that? A climate feedback mechanism. What is a climate feedback? A climate feedback is the response of the climate system to a climate disturbance and the climate variable that has caused it. Okay, you know what a loop is. Okay, a loop is a connection. Okay, a loop is connection between essentially the climate variable. It's a little sketch here, changes in the climate variable. Okay. Resulting in a heat flux anomaly. Okay. And this heat flux anomaly will lead to a temperature change. Okay, a climate disturbance, a temperature change. Then the question is, will this temperature change increase the change in the climate variable, increase the heat flux anomaly? Okay. And we call positive feedback loops the situation in which the magnitude of both the cause and the response increases, destabilizing the climate. A negative feedback loop has a stabilizing effect on the climate. Okay, so I'll give you one example. If Arctic ice coverage decreases, will this trigger a climate disturbance that can further decrease the ice coverage? What do you think? So let's talk about key climate feedback mechanisms. Okay. And there are several of them. Okay. So the key ones are the water vapor feedback, which is related to evaporation. Okay. How much water vapor is in the atmosphere? The second one is the albedo feedback. It's to do with the ice coverage and also type and extent of clouds that we have. There are other cloud and lapse rate feedbacks that I will not discuss in great detail, but I just list them for you. There's a solubility feedback, which involves the ocean, which is about the air-sea CO2 exchange. There are vegetation feedbacks, and indeed there are anthropogenic feedbacks. Okay, and I will just briefly describe some of them. Okay, water vapor feedback. You know that the water vapor is a key greenhouse gas. Okay, so there's a feedback mechanism. Okay. So, starts off, if you have a warming effect, okay, the global air temperature increases. Okay. You get enhanced evaporation, okay, through a variety of effects. Essentially, the air can hold more water vapor, more moisture, and so you have actually enhanced. You enhance the amount of water vapor in the atmosphere. Okay, so you get an increased greenhouse gas effect, and you get a cycle that enhances. Okay, you get a positive feedback loop. And then the general question is, why doesn't this feedback make the Earth's climate unstable, or does it? What limits the positive feedback? And it's amazing to know that actually we had a runaway water vapor feedback on Venus. In Venus, this runaway effect actually, led to a temperature increase without, essentially without bounds. And this is shown in this little sketch. We try to understand this effect. Why doesn't it happen on Earth as compared to Venus. What balances the water vapor feedback? And if you look at that, it's what this graph tells you is, well, there's actually something happening if you increase the water vapor pressure, and you actually get an Earth, and it also is a function of temperature. There is something happening which is related to cloud formation. Okay, so on Earth, the albedo effect from clouds and ice operate to balance the water vapor greenhouse effect. So you have balancing effects. You have other mechanisms that put a limit to the water vapor feedback. Okay? And on Venus, you don't have that transition. You don't have condensation and the formation of clouds. That's why you had a runaway water vapor feedback on Venus. So, next one is the ice albedo feedback. Okay? And you already guessed it right. The ice albedo feedback is related to the albedo. Okay? It's a positive climate feedback. If you have more ice area, you have more reflection of solar radiation, you have reduced heat fluxes, so you get more ice. Okay, so it's a feedback that includes the temperature, the coverage of ice, snow is also involved, and the albedo effects. Dominant feedback during ice ages. Okay, what limits this positive feedback? Well, there's no real limit other than you can reverse to a warmer climate through emission of massive amounts of CO2. In this case, not by humans, but through volcanoes. And this is shown here on the next graph, a little sketch, okay, which shows the transition between snowball Earth effects, okay, maximum ice coverage, and no ice coverage. Okay, you have two different situations here, whereas one transition is triggered by the ice albedo feedback, making it colder and colder and colder, and having the ice extending further and further. And the other one is the emission of CO2, which actually brings it back into a stage of no ice. Okay? All right. We have a variety of cloud feedbacks, because clouds come in all different type of shapes, okay, which are shown here. There's cirrus clouds, cumulus, and stratus. And you can imagine that these stratus type of clouds have a high albedo, because there are continuous white surfaces, as you can see. Okay? So clouds reflect solar radiation. It's the albedo effect. The albedo range is 0.2 for cirrus clouds to 0.7 for stratus clouds. Clouds do not absorb much solar radiation, but they absorb terrestrial radiation very effectively. Most clouds, except thin cirrus clouds, absorb and back-radiate terrestrial radiation. So that's the greenhouse effect. Okay? And now just a summary. Globally, clouds contribute to 50 watts per square meter of solar radiation reflected to space and 30 watts per square meter absorption of infrared radiation. So overall, clouds have a net cooling effect of around 20 watts per square meter. Okay? And changes associated with clouds are very tricky it's not easy to predict changes. Let me say that. Okay? All right. Another feedback mechanism, and this one is an important one too, it's the solubility feedback. It's about the maximum amount of gas that can be dissolved in the upper layers of the ocean. It's about the equilibrium. Okay? And this is what we call the solubility. And the solubility depends on the sea temperature. And if the sea temperature changes, the situation can move away from the equilibrium. You can have an oversaturation leading to an outgassing of CO2, or you have an undersaturation which leads to a CO2 uptake. And the solubility feedback has two different phases. You know, where you can have a temperature increase, okay, decreases the ocean solubility, leads to an outgassing of CO2, enhancement of the greenhouse effect, temperature increases, is a positive feedback. Or you can have another positive feedback where the temperature decreases, okay, you have the ocean takes up CO2, reduces the greenhouse effect. So you can move in either direction. However, this is one example of a solubility feedback which can actually start with a temperature increase. You get a temperature increase first, like changes in the orbital cycles, which triggers outgassing of CO2 and then kicks off the feedback and adds more and more CO2 into the atmosphere. So it's very fascinating. It's a very important feedback mechanism, in particular in the Southern Ocean, noting that the Southern Ocean, has a large coverage covers large parts of Earth. So there are other feedbacks which are just briefly mentioned here. We have the lapse rate feedback. It's the influence of the vertical temperature structure in the troposphere on the magnitude of the greenhouse effect. We have other ocean feedback mechanisms involving plankton production. We have vegetation feedbacks. There's one shown here in the sketch. And we have anthropogenic feedbacks. It's like, well, do we decide to stop emissions of greenhouse gases? There are important feedbacks between humans and the climate system. And I think that this concludes the second part of this lecture.